she obtained her engineering degree at the University of Belgrade and a PhD at Caltech. And she has graduated 50 PhD students.
I didn't feel old when I turned 50, but when I graduated Frank, I felt very old.
And she's currently advising 16 doctoral students in areas of microwave engineering. She has received numerous awards. She's a fellow of the IEEE. She has received 2 prizes from the MTT Society for Best Journal Paper Awards. She holds the White House NSF Presidential Faculty Fellow Award.
Yeah, you skipped that.
Okay. and actually, what I wanted to say is that aside from being an exceptional scientist, she's also a very distinguished educator. She has received the MTT Distinguished Educator Award in 2013. And personally, she has inspired a lot of our work with Anna in the microwave field. So it's a great pleasure to have you here. So yeah. The floor is.
That's a very kind introduction. It's great to visit you, Apostolos and Anna have been inviting me for a long time, and it's great to be here and see you all. And I've decided to give you first a little bit of an overview of my university and the group and the projects that we do. I cannot talk about all of the projects because there are many. 16 students means roughly 16 different theses. And so I've chosen some topics that I thought would make sense and that would be interesting, but I'll give you a list, and so if there's something else you're interested in, just let me know, and afterwards we can talk about that as well. So the University of Colorado is located at the foothills of the Rocky Mountains at 2,000-meter elevation roughly, and I'm advertising our geography. It's a beautiful place to live, but also a good place to work. The university has a very good department in physics. We're ranked #1 in the world currently in atomic and molecular optics, with 5 Nobel Prizes in the past 10 years roughly in physics, ultra-cold atoms, Bose-Einstein condensate mainly. We have now about 30,000 students. They've allowed us to expand a little bit, although the state tends to limit the number of students. And we've had the largest NASA funding in the country for the past 20 years. So there's a lot of NASA work. Many of our students launch satellites and work on space missions. The Boulder is ranked by Forbes magazine as the smartest city in America. I have no idea how they determine this, but I think it's because everybody likes to live there, and so they get a master's degree in, say, psychology, and then they become waiters. And so the average waiter has a very high degree. Doesn't mean they know much. The nice thing for me is that there are a number of national institutes that are extremely good, and I have a lot of colleagues to work with. So it's a very vibrant technical community, and there are also a lot of high-tech companies in the area. Primarily NIST, which is the National Institute of Standards and Technology, is located literally 3 minutes by bike. So my department is here roughly. This is always the dominant football stadium that, if anybody asks me, should be moved to Denver. And NIST is somewhere right here, and so it's extremely close, and we have kind of an open lab policy. And I'll show you at the end, if we have time, a project in terahertz imaging that I've done with one of my colleagues there. We always have joint projects. I've worked with the quantum electronics division on Josephson junction voltage standards, on atomic clocks with them, and I have a continuous effort in terahertz. ANREL is the National Renewable Energy Lab that's located in Golden. It's about 15 minutes drive. A lot of my colleagues bike there. It's a pretty hefty bike ride. And so you see the scene where they do measurements of various wind turbines. There's a lot of photovoltaic work and biofuel work. So I have a project with NREL currently in PVs. And then it's a mecca for meteorology. So NOAA, NCAR is the National Center for Atmospheric Research. Series is it's environmental, but it's really climate related. And so there's a lot of opportunities to work on weather radar and LIDAR if you're interested in that. And finally, the U.S. Geological Survey is also located in Boulder. Colorado is a mining state, and so in fact, we have a school of mines that's separate, that's in Golden. So please visit if you can, or if it's in your way, just let me know and stop by, and I can arrange for you to go into NIST. Nowadays, we have to get passports approved and things, but if you want to see the clock that keeps the world time, it's located just a few minutes from the university. It's just in a room. There are other more interesting labs there, I think, but it's kind of nice to see the world time. So these are snapshots of 3 generations of my students. We tend to go on on trips where there are large antennas, just because they tend to be in nice places also. So this one is the VLA, that's the newest group, so a few of these have graduated already. It shows about 6 of the antennas of the very large array, which is currently the largest radio telescope in the world. It has 27 dishes, 9 in each arm of a big Y. And it can be moved. Each dish is 25 meters in diameter, and they have receivers, cryogenic receivers, that operate into W band. The dishes are not smooth enough to go above that. And they have them. It's really interesting. If you get a chance, it's worth visiting. It's a little bit far away because it has to be far from every noise source. So if you go from Albuquerque, it might be about an hour to Socorro, where the operations center is, and then another 40 minutes out in the desert. But it's really worth seeing. So they have these antennas on large rails that you can move to change the baseline. It's an interferometer, and so when they're far away from each other, you see deeply in space, and when they're with less resolution, and when they're close, you get high resolution but close. And so this is how they get their funding from Congress. They basically put them in the farthest constellation called D, and then they superimpose it on the map of Washington, D.C., and it's bigger than Washington. And then they show Congress, and they say, look, we have an antenna bigger than Washington, D.C., and then they get money. It's a good strategy with politicians. And the picture right here is in Puerto Rico at the Arecibo telescope. I'm actually in the feed. I'm not in the picture. This feed, so there's a dish here that's one of the few spherical dishes actually in the world. It's 305 meters in diameter. And the feed is a 3-story building. It was really a little scary to walk here. It was windy. And so you walk this way and then descend into the feed to see the receiver. It's really cool. This one is managed by Cornell, and it's a National Science Foundation instrument, so they keep saying that they're going to cancel it. If you get a chance, go see it. And this is on top of Mauna Kea in Hawaii, where there are a lot of millimeter wave telescopes. So I have a few colleagues, Professors Kuster, Filipovic, and Gajewski. Professor Kuster is an analytical electromagnetics theoretician, great resource. He'll be retiring fairly soon, but he's one of those classical, knows everything, reads Russian papers type of guy. Professor Filipovic came from Volakis' group in Michigan, and he is an expert in broadband antennas, any antenna you can imagine. And Professor Gajewski does a lot of remote sensing for global climate prediction. He has experiments that fly in Alaska on the South Pole, so very large experiments. And we together have over 40 PhD students and a number of masters, and a very good curriculum in microwaves. So, and they're really all great to work with. It's a good group. I'm very happy there. We're complementary, but different enough but similar enough that it's nice to work together. So these are some of the projects that we're currently working on. I have a lot of my students work currently on high efficiency transmitters for communications and radar, number of different approaches, and I'll show you a little bit of an overview of this work. By the way, if I'm going too fast or too slow, please tell me. I don't know your background, and so I could be doing either. Okay, so if something is unclear, just wave at me, or if you want to change, I can adapt, okay? We've also been doing for a number of years work in microfabricated 3-dimensional components, so very high quality passives for broadband typically applications, and so I'll show you some of those projects as well. And then we've been working on wireless powering for many years, and I will not talk about that because you have excellent expertise in the Institute, and I think that Apostolos and Anna have heard my talk on this many times, so I don't want to expose them again to this topic. But of course, if you are interested, there are a number of papers in this. And I have 2 medical projects. I'm not an expert in biology or medicine, but they need help. It turns out if you know microwaves, everybody needs you. It's great. And one is in a very interesting project in microwave radiometry, which is there's no way currently to measure non-invasively internal body temperature, which is the core body temperature is defined as the temperature of the aorta coming out of the heart. And it turns out there's many medical reasons why you would want to monitor core body temperature relative to the outside especially. And so we're approaching this by microwave radiometry, so measuring black body radiation from different layers. It's difficult because the body has tissues that are very complex electromagnetic materials, and everybody is different. So there are a lot of calibration challenges involved. And then we also have a new project in redesigning cavities for magnetic resonance imaging systems. Currently, if you want to get higher resolution, you go to higher DC magnetic fields that sort of prepare the hydrogen atom for its resonance, and then you apply a AC field that resonates the atoms, processes them. And the higher the DC magnetic field, the more resolution you can get. But a higher DC field is accompanied by a higher resonance frequency. There's a coefficient there. And so, for example, the highest currently clinical used instruments are 3 Tesla magnets. And that goes with 128 megahertz resonant frequency. So imagine you have a bore where a whole person lays down, right? It's metal, so it's a cavity. Normally, it's not a good waveguide at 128 megahertz, so they use quasi-static techniques, coils, to excite the magnetic field. But if you put a dielectric body, a person that has an epsilon of about 80, suddenly you change the modes a lot. You're loading the cavity and you get traveling waves. And so you can get nulls because it's actually traveling but standing wave because you have metal on the other end too. And so they have a lot of blind spots in the imaging. And so we're working on redesigning this cavity, the wall, as well as the exciters and some loading in order to make as uniform of a magnetic field as possible inside the body. So it's quite challenging. We're working with the Harvard Medical School on this. I mean, I have the funding, but they can do the medical measurements once we do the redesign. So, and then some terahertz electronics. We've had a lot of very interesting projects in the recent past. So these are, for example, the second one was finished last month. So they're very recent projects. One is in near-field hyper-resolution microwave probing for buried things. So for example, let's say you have an 8-layer CMOS circuit and you want to find out if there is a problem at the 6th layer. You can use a low microwave frequency with a near-field probe, and we get resolution that to optics people sounds really crazy. Lambda over 20,000. But it's near-field, and lambda is huge, So it's really limited by the size of your probe. And that was an exercise in low-noise electronics. It was a very, very interesting project. And then also multi-beam antenna arrays that I want to show you, actually. I think you'll be interested in this. And then we've done a UWB radar, which I would love to show you. We made a radar that can detect a supersonic target at 7-meter range, but it got classified after the student defended. So the thesis had to be completely changed. Oh, it was a miserable experience. They basically didn't believe, Sandia funded this, and they didn't believe we would do it. So they didn't tell us ahead of time that it could be classified. Yeah, it was totally miserable. I never want to do that again. And then we've done Josephson junction voltage standard. So the volt is defined with a quantum device. A Josephson junction is a cryogenic device. If you just think of it as a black box, you put HF in, and you get a constant times a DC voltage out. And it's quantum defined, so meaning extremely precise. But the coefficient is microvolts per gigahertz. So you need a lot of gigahertz and a lot of junctions. It turns out they are biased with current, so you put them in series. You need a lot of tens of thousands of junctions in high frequency to get a reasonable standard. If you make too small of a voltage standard, you have to amplify it after that, and you add noise, and it's not a good standard anymore. So we made a 10-volt DC standard for NIST and made some good progress with an AC standard. This shows that you probably can't see it, but this is a chip. It shows it has 10,000 Josephson junctions in series in a microwave dividing network, and its broadband works out to 25 gigahertz or so. The challenge there is that the technology used for making Josephson junctions is very different than any other microwave technology, any MMIC. And so we had to kind of reinvent some circuitry that would work in that technology. But the advantage is they're cryogenically cooled. They're at 4 Kelvin. So you have like perfect inductors, So there were pluses and minuses. It was quite interesting. Okay. So this is totally basic, but I just want to tell you what kind of things we worry about in my group at the high level. Every microwave system roughly has this block diagram, and there are always trade-offs that you make. At the transmitter, you trade power with efficiency, with linearity, with bandwidth. It's extremely difficult to get a power amplifier that can be very efficient, very broadband, very linear, and have enough power. Basically, you can't do it. So we are working on combining, you know, making it high power and efficient, and then adding linearity and adding bandwidth, you know, depending on the application. Similarly, in the receiver, you always trade noise sensitivity, dynamic range, and bandwidth, and I won't talk too much about receivers, but in all of our radiometry and imaging, you have to worry about that. And then there are passive circuits, you know, there's the antenna, there are a bunch of matching networks, all of that, you need high-quality passives. Somewhere, there's a line where you end up going to digital. It's not very clear where this line is for a given application. In fact, you know, there'll be people that say everything should be digital, and that's certainly incorrect, because there are many applications that if you move the digital out to the antenna, you completely lose dynamic range. You simply don't have enough bits at high frequencies. And so I like to worry about this dashed line, where it goes in the system, in order to optimize the real prime resource is the power that you're putting into the system. You know, so what will make it the most power efficient? And it turns out that a lot of times you can even do processing in an analog way that will give you good dynamic range and use much less power than if you did it digitally. And so that's kind of my big picture that my students don't understand until they're almost done, you know, because every project has this element in it. So I'll tell you about some passive and active circuits that optimize this parameter in a systems context. So the first topic I'd like to address are passives, because they're easier than actives and they're easier to explain. And this is also a really cool technology that I think is very promising. I'll show you technology by one company, but there is no reason that many people cannot do it. They do have a patent on a photoresist, but you know, there are many other ways you could do it. We've used them. We started, basically we helped them start with the giant DARPA project where they were our subcontractor. I have found this to be a very efficient way of operation. I don't know if you know how funding is done in the US, but usually the military has money because a lot of our taxes go to the military, but then the military is obligated to fund research. So it's actually a very efficient system, at least was until now. They're changing all of that. But the military will then typically fund large subcontractors like Raytheon, Northrop Grumman, you know, these huge companies. And then they fund smaller companies and universities, and they put universities kind of like, I don't know, just because they have to and they never expect to get anything. But in the end, the universities tend to do a lot of the work, you know. So DARPA has figured this out, the people with money, and so often I'm able to be the prime. I get the money and I pay the companies. And this is super efficient because then I can violate design rules. You know, we can really push technology, and it's been a very good model. If I can talk DARPA into doing it, it's by far, and for them it's much cheaper because my overhead is a lot less. Raytheon's overhead is 250%, mine is 50. It's a huge change, you know, huge difference. These are just business tricks, you know. Anyway, how do you get this DARPA funding? You come up with a very simple formula that everybody can understand, including a program manager. But to get the simple formula, you have to know fundamentals extremely well. So here's one example that is a very good tool for students also to get them convinced that they have to learn fundamentals. So imagine you have a coaxial cable. This happens to be a microcoaxial cable, meaning it's 250 microns in radius. It has a square cross-section. You can pick any cross-section you want. It is square because it's deposited in layers. So you deposit a layer of copper, then another layer of copper with some photoresist, another one where you define the center conductor and so on, and then you evacuate the photoresist, and you're left with the center conductor basically floating in air. It's not really floating. It's supported by thin plastic strips, but there are not many of them, so they take up a very small volume. And why do you want to do that? Well, first of all, it's a planar technology, so in principle it's cheap. Currently, it's, I think, too expensive because they have low volume. They just basically started. There were 2 generations of thesis, and that's it. But they're now commercializing this, and it's, I think, very cheap, actually. So these layers are, 50 to 100 microns thick with a good aspect ratio, and that's really the intellectual property of this company called Nuvotronics. They figured out how to make a photoresist that can do this fat deposition. So, but we did all the microwave development for them and all the testing because they didn't know any RF. They were chemical people, So if you have a coaxial cable, any cable, and you go through the transmission line equations, it turns out that for a low loss cable, you can express the attenuation coefficient alpha. So power decays along a long cable as e to the minus 2 alpha times the distance, RZ, whatever you call it. So these two terms physically are based on dielectric losses. Here, this G prime is the conductance per unit length, so it's what you lose in leakage through the dielectric, the white thing in the black BNC cables. And does everyone know this formula? So I don't have to explain. Hello? No, well, I'll just briefly go over it because it's actually not intuitive. So this is dielectric loss, this is conductor loss. Okay, this is skin effect, bad metal, whatever. So let's say that we have a perfect dielectric, so this doesn't exist. Okay, perfect dielectric. Term goes away. Let's look at what the attenuation coefficient depends on. R prime is the resistance in the metal. Not much you can do about this, right? If you use copper, there's a number for this. If you use a certain frequency, this will change because of the skin effect, okay? But you're stuck. But if you look at this term, the top is capacitance per unit length, and capacitance always depends on dielectric constant. So for example, for a circular cable, it's 2 pi epsilon divided by ln b over a. Okay, b over a are dimensions, so it depends on dimensions and shape, like all electromagnetic things, and materials. So that means that this is a square root of epsilon relative. So that means even if I have a perfect lossless dielectric, I still have the lowest loss when I have air, which has the lowest epsilon relative. And this is how we got, I don't know how many $1 million to develop this technology. Because that means that we can justify we want to do it in air because it has the lowest loss, okay? And the reason fundamentally is because of polarization charges that are in the cable. So why is this also nice? Well, it's TEM, that means no frequency dependence, a plane wave. It's non-uniform, but it's a plane wave. Up to 450 gigahertz for a 50 ohm cable, so very high. Actually, you wouldn't want to use it above about 100 because of losses. You're better off with waveguide after that, and I'll show you some waveguide circuits as well. But if you try to buy a cable, like, do you guys, what's the highest frequency network analyzer you have? Okay, so you have 2.4 or 1 millimeter?
We have 1 millimeter.
Okay, so those cables, 1 millimeter, the higher you are in frequency, the smaller your cable, otherwise you excite bad modes, okay? And so the 1 millimeter cables cost, what, $5,000 a cable? I mean, it's ridiculous, right? And it's not the cable, it's the connector that costs really money. So we wanted to make something where you can scale this and have it work at very high frequency, but have it, you know, it's fairly easy to contact. We developed contacts for this that are fairly easy. Anyway, it's high frequency. It has extremely low loss. We've measured less than 0.1 dB per centimeter out actually to 50 gigahertz. And the isolation is extremely well. These are shielded. The holes here, you might wonder what the holes are for. They're to evacuate the photoresist, but we designed them so that they don't affect the behavior of the coax well above a few hundred gigahertz. And you can change them for above that, but as I said, I wouldn't use them above that because they're too lossy. But if you put 2 of these cables right next to each other with the holes there, we measured minus 70 dB coupling. So basically, I don't think I can calibrate better than that. It's within my calibration. So they're extremely well shielded, and that means I can make very dense circuits. I don't have to worry about coupling. And that's very powerful because on a normal IC or in a hybrid circuit, you cannot do them very densely. You'll have a lot of electromagnetic coupling. This is a 6-inch silicon wafer that's used just as a dummy wafer. It's nothing special. You can do it on anything that's flat. So they've done it on various other substrates as well. And it shows a number of, I don't know if you can see, but it shows thousands of these components on a 6-inch wafer. They're made in copper. And later we can plate them with gold if we don't want them to rust. That's a fairly straightforward process. So for an engineer, the nice thing, it's like a box of Legos suddenly, because suddenly I have new tools. I can make totally new circuits that I couldn't make before. For example, because it's a closed structure, full wave finite element, you know, HFSS, gives me perfect agreement with measurements always. You have to know a little bit what you're doing. Then I can make a very large range of characteristic impedance in the same process because, so this is the typical stack up with 11 layers. They have a 5-layer and an 11-layer process that we've developed. You can, in principle, make any number you want, but it's practical to stick to a certain geometry. In a fab, then you can have a very well-controlled process. And so with this, if you change the aspect ratio of the you change the capacitance per unit length, and so you change the impedance. And we've measured from 8 to 140 gigahertz, 40 ohms. This is a huge ratio. If you think about normal microstrip, it's 20 to 90 ohms roughly. Maybe you can get to 100, but if you, the ratio is what's relevant. You know, in one case it's a ratio of 5, and in this case it's whatever 140 over 8 is, so it's a very large ratio, almost 20, you know. So that means I can make circuits I can't make in any other technology. And then hybrid integration is fairly straightforward. This shows a picture of bias T that works from about 4 to 18 gigahertz for a power amplifier. And the thing here that looks like a resistor is actually an inductor, and it's 3-dimensional. So it goes outside like that, it meanders, and it can handle 5 amps of current. We've tested it. I think my students blew up a bunch of them just for fun because it's pretty fun to watch them blow. As you increase the current, you get the heating and also magnetic forces, and the thing just warps, and then it goes, I think they've blown at least 10 just so they could see how they blow up. But you know, you get a lot of them, so it's okay. And then we've made these holes in the coax, so we make openings and connections. We call them sockets, like the wall socket, to put surface mount components. So this is a low temperature process, which means you cannot make good capacitors. But it's good that it's low temperature because you can combine it easily with other processes without affecting them. So you can buy extremely good surface mount elements, and then as long as you know the package, and these are usually standard 0603s or 0402s or you know, some standard package, you can make a perfect receptacle with very low parasitics and just drop the device. And it's not hard to do, even I can do it, and I'm a lot clumsier than my students usually. So you just put some silver epoxy, or you can deposit solder and then put them in and heat them. It's fairly straightforward. So this has a blocking cap, a choke, and then a short to ground for the RF. And it worked very well as a bias. Steve could handle a lot of current. This is a cross-section, so you can see these little plastic straps. They're polymer straps. I'm not allowed to tell you which polymer, but if you took guesses, you would guess, I think, third time, or first to third time. So it's a standard polymer. It takes less than 0.1% of the volume, so it doesn't contribute to the loss, but it does contribute to the power handling. Because if you heat this polymer above about 120 degrees, it undergoes a glass transition, basically changes structure, and then it's even worse than it was before. So the whole thing collapses. But we've tested this out to 100 watts at 2 gigahertz. So these small cables are can handle surprising amounts of power. It turns out that the field breakdown is not an issue. You can, for various reasons, it's thermally limited, really. And we've tested it broadband with 20 watts of power. I don't have 100 watts broadband, so it's a good device. Here's an example of what you can do. This is a Wilkinson, very broadband Wilkinson divider. A Wilkinson divider, you put power into one port, you get equal split on the two others in phase. And usually it has one section of quarter wave lines, but if you want to make it broadband, you add sections. So this is a 5-section. These little gray things are resistors that are part of the design. And this just shows the result. So these are the reflection coefficient and the isolation on the reflection coefficient on the 2 ports and the isolation. And you see that from 2 to 22 gigahertz, this device works, okay? This is a huge bandwidth, 11 to 1 bandwidth. It's over a decade, okay? And the loss is extremely good. So this shows on a scale of 1 dB. So ideally it would be minus 3 dB, but because it's a long device, we have 0.4 dB loss. And it's very nice and flat out to 22 gigahertz and meets our predictions. This here is a very relevant thing when you're doing dividers. It's how well the 2 ports are matched in amplitude and phase. And the scale here tells you that it's extremely well matched. For example, the phase is within 2 degrees or less. It's basically within half a degree. You can't even measure it. It's as well as I can calibrate. So it's an extremely high quality device, but you may look at it and say, oh, I don't like it. It's very long and narrow and it doesn't fit in my circuit. Okay, I don't like that. Well, then you can bend it. Okay, so this shows because it's very well isolated, you can bend it and do whatever you want as long as you analyze the parasitics due to the bends. And so this shows one that was bent. Here's a photograph. Actually, these are two slightly different ones, but it's the same general idea, and this shows the measured data, so it works just as well as the other one. And we make our standards in the same technology so that we can get very reliable measurements. And then we, of course, wanted to make something active because passives alone are not very useful. And so this shows a gallium nitride chip from BAE Systems, so I can't give you details. They're super secret about it, but it's actually not very impressive. It's just a gain stage that's broadband. So it works from about 2 to 10 gigahertz is its nominal operating range. And you see the backside of the chip. So these holes are vias that are from the sources. And it's flipped. So what we designed are two coaxes that are 50 ohms here. This is a pre-matched chip, so it's designed for 50 ohms. And then we also designed the bias lines in the same technology. And then we put the chip down like that. So this just shows a through line, and this is the measurement of the through line, so it's very flat. And then we measured the chip in that, then we put the real chip. And what you see here are actually two lines on top of each other. There's a red and a blue here, and a green and a black down here. One set of data is for on-probe wafer measurements, and one is in this configuration. So basically, you can design stuff without any parasitics, which means I don't have to do bond wiring, which is really great. If you've ever done wire bonding, you know what I'm talking about. If you haven't, you should try, and then you'll know. So then we made a bigger system with actually two chips to do some power combining here. So I can't show the chips, but they're sitting right there. So what do I have here? I have a Wilkinson divider that splits the signal in two, then splits it again. So I have 4 inputs. These little circular things are matching networks. The input of a typical gallium nitride amplifier is about 12 ohms if it's broadband, 10 to 12 ohms. And I have a 50 ohm system, so I need to match 50 ohms to 12 ohms. And the way this is done is a little bit non-standard. This is called a coaxial transformer. So are any of you maybe amateur radio operators? Oh, you should be. It's a lot of fun. And furthermore, when you have an extra license, the top license, and it's trivial for electrical engineers, you can study 1 hour and get this license. You have to know what the Smith chart is for the last one. But you get that, and then you can legally emit a lot of power at practically any frequency. So in my lab, we can make a lot of power and always be legal, because I make all my students get this too. So they hate me in the beginning, but then later they don't. And they're like, oh, you're so old-fashioned, we've got email, blah, blah. And then, government of Egypt decides to interrupt email, and right? But they can't interrupt radio. It just bounces off the ionosphere. So, and in the tsunami in Japan, the amateur radio operators are the one that saved a lot of lives. And also we have big forest fires often, and they're very active. It's great fun. And these are older people, retired typically. They're great fun. Yeah. Total nerds, complete nerds. So anyway, let me show you how this coax works, because it's a really cool device. Have you ever used this? Microwave people? You have?
I can see, yeah.
Have you made them?
No, I didn't.
So you can make them out to high UHF by taking two coaxes and just soldering. But beyond that, it's very hard because you can't control the connection very well enough. So what you do is you take two coaxes and you take the outer conductor of the first one and connect it, make it the inner conductor of the second one. So what you do at the input is basically you have the two voltages in series. So you get V plus V, that's 2V. And at the output, you combine the current. So you get 2I. And so that means the impedance ratio is 4. So from 50 ohms, you go to 12.5, exactly what you need, for gallium nitride. The advantage of this device, so it works very well, it's very broadband. In other words, the length of this line doesn't matter as long as they're the same. And the group delay is extremely good because it's so small. So if you made a standard, if you look up in book, like in Dave's book or something, you have these tapered lines for broadband matching. So a typical one is Klopfenstein taper, and if you made it in this technology, it would be 6 centimeters long, and it would have a group delay measured in the hundreds of picoseconds. But if you make it, this device has a flat group delay, and it's an order of magnitude less group delay. That means you can send a pulse, and it will not get distorted. And not to mention loss, right? This will obviously have much less loss than that. So it's really cool, and we've made many different transformation ratios with these, and we've used them for a variety of different things. So, and many people don't really know that you can do this, so I'm telling you in case it comes up. It's very broadband. So then we wanted to actually, we've used this technology for broadband, which I showed you, and we've done many different components of millimeter waves, which I will skip. But I want to show you a very interesting application. NASA came to us asking for help for the next generation landing radar. Is this of interest? You have to tell me if something is boring. I have a lot of topics I can skip easily, you know. But have you seen the Curiosity landing mission on Mars? You can go to the NASA website. It's very entertaining. Go and look at it if you haven't. So basically what happens is a parachute deploys, and then somewhere down the line, about here, the radar gets activated. And this is a multi-frequency radar. It's a phased array. In the Curiosity mission, they used 37 gigahertz, I think, Ka band at any rate. And it was the size of a table. It was about 1 meter by 2 meters, almost in this thick. And that's a bad payload for that's very large, but they couldn't make it any smaller. It was a phased array, so it swept the beam multiple frequencies, so it did Doppler. It looked at the speed of the vehicle as it was landing, and it also used the multiple frequencies to detect obstacles. So it didn't want to land the vehicle on a big rock. It looked for something flat, okay? And so NASA wants to shrink this because it was too much weight and mass. And they asked us to do it somewhere between 150 and 200 gigahertz, so that the size of the antenna would shrink to about this big compared to the whole table. So, okay, fine, you can shrink the antenna, and it's nice. On planets, you don't have the crazy atmosphere we have on the Earth. On Earth, you would get no penetration. It would all be absorbed by water. But there's no water on Mars, so you can just use any frequency you want, pretty much. And the problem, of course, is for a phased array, you use phase shifters and amplifiers and things, and that doesn't exist at 150 or 200 gigahertz. It just simply, you don't have any circuits. The thing that does exist is a voltage-controlled oscillator at a lower frequency that you can multiply up. So it's not very efficient, but you can make it, and people make them. And so we said, all right, that's the only thing we have, so we have to think of an antenna array that will scan the beam, but only use that kind of a component. And there is a class of antennas that are used, that can be used like this. They're fed in series, so this shows a linear series fed array. A linear series fed array that has a line in between each element, and as you change the input frequency, it changes the phase between the elements, and that means that you steer the beam. So it's very simple in principle. Many of these arrays are made in waveguide, and they're sitting in front of airplanes in the nose, but they have a short circuit here, so they're a standing wave. They don't steer. They just use it as a simple feed. So this is a little bit different, and it is used. I mean, I've seen them published before, but nothing above, say, 10 gigahertz. It turns out you have to dissipate about 10 to 15% of your power in the load to get a good uniform distribution of the power. So what does this look like at a high frequency? Well, this is implemented in the same technology, except now it's not microcoax. Because of the high frequency, it's better to do it in waveguide. And also, you want dispersion. Coax is not dispersive. It's TEM. It's a plane wave. You want dispersion because the more dispersion you have, the less frequency shift you need for a given phase shift. So it's one of the few times in life that you actually want things to be frequency dependent. And this shows a waveguide implement, so it's very small. This here at the end is a transition to a standard flange, so we can use it for measurement, to measure it, to characterize it. So that doesn't exist in the final one. I'll show you the final one. This shows a linear array with 20 elements. These are slot antennas, and they're arranged like this because the current shifts phase by 180 degrees every half wavelength, and so this means that they're all in phase. And these plots just show that it's designed properly. This is measured versus simulated reflection coefficient and transmission. And then this shows the VSWR. So basically it works. And then how does it steer? Oh yeah, when you work at millimeter wave frequencies, everything is about holding things. The electrical stuff is easy, you know, it scales if you have the technology. But then you have to put it together, and it's very sensitive to placement. So it's all about holders. So you have to befriend a mechanical engineer and have them help you. And this slide is about all kinds of things we had to do to actually hold it properly and align it. And we measure it in a quasi-optical setup. Anyway, it's a mess. Okay. But this is the result. So you have a set of beams that scan as you change frequency from 130 to 180 gigahertz. That was the band we picked, and that was just based on the size of the waveguide that was dictated by the layers of the current, you know, process. So this is a normalized pattern. So the gain does vary a little bit, about 2 dB, but predictable. I don't have the plot here, but it's in the papers. Actually, one paper. And then you can see that we can predict the patterns. I picked 2, and here's simulation and measurement. It gets too crowded if you put it all in one. And we got scanning of about 1 degree per gigahertz of frequency change. So it's good, it worked, it met their specs, but I wasn't happy. I thought we could do better, because you ultimately need a VCO that changes a lot, so it affects your gain. And so what we did in the next version is we made the waveguide with a slow wave structure, so corrugations at the bottom. This was a lot of fun. So you can make these corrugations, the process lets you make whatever you want, basically. And if you look at so the scan angle you would get with no corrugations with a regular angle looks like this versus frequency. And if you make the corrugations, you can make it as much as this green line. So that's the one we made. This is just a parametric study of how we chose it, you know. And indeed, these are the measured patterns on a much larger array. This is a 2-dimensional array now with the combiner network that we delivered to NASA. It's 32 by 32 elements. We also made some smaller ones so they could combine them differently if they wanted. And now we got 2 degrees per gigahertz, so we doubled the scanning. In other words, we shrunk the frequency by a factor of 2 for a given scan angle. And unfortunately, I don't have these anymore. I had to deliver all of them, so all I have is the picture I'm showing you. It's very sad when you have to part with a piece of hardware that you've spent 2 years on. So this shows a measured beam in 2 dimensions. This scans in 1 dimension. They want to do 1 for one and 1 for the other for systems reasons. And this shows that we can predict the patterns. So this was a really fun project, and it will fly on the next planetary mission if Obama ever approves it. This is NASA is very political. So I don't know when we started.
I think power amplifiers.
Are you interested in power amplifiers or in terahertz imaging or what? I can talk forever about this. Not forever, but many hours. Power amps? Okay. So a lot of my work is currently in power amps, to a point where I think I'm going to slowly get out of it because I can't think of new thesis topics, you know, that are sufficiently different. And also, when you do a good job at it, then industry comes and they all want you to repeat this for them. And I keep telling them, this is not a good thesis. I don't want my students to have the same thesis over and over again. So we're working on various approaches, some mimic design, some supply modulation, some harmonic injection, DC, all kinds of things. But I picked a few topics that make sense. If you have any questions whatsoever, I have a lot more about this. So if you haven't done power amps, this is just a brief introduction. In a class A power amplifier, what you do is you have a sinusoidal voltage and a sinusoidal current across the device itself. And when I say across the device, it means come in. Oh, you like the door? Okay. Or do you need the room? Maybe he needs the room. So what is relevant is the current and voltage at the current source inside the device. And at microwaves, it's actually hard to penetrate that to get to that point, because you have a lot of parasitics due to packaging and pads and things like that. So that's a big part of what we do, is trying to de-embed and get into the device. But that's what's relevant, because ultimately the heat that's dissipated is the product of the current and the voltage, right? So this gray part that you see is V times I, that's your heat. So that's what you want to minimize. One way to do it is not to conduct for a period. So the red is the current, and I've decided to shut the device off. How do I do it? I bias it so that when you drive it with a big signal, it shuts off. It's just not conducting in the negative portion. And now you have much less heat dissipation. So this would be a class B amplifier. And when you conduct a limited part of the cycle, it's class A, B, B, C, and so on. So that's good. You've reduced it a lot more. So this has a theoretical maximum efficiency of 50%, practically a lot less at microwaves. This has a theoretical efficiency of pi over 4, but practically a lot less. Now, can you do anything else? Well, yes. If you think about it, you can reduce the gray part by pushing this a little bit. So not making it sinusoidal, but trying to make it more like a square wave. Okay? How do you do that? Well, clearly, when you look at this, you see it has more harmonics, right? To make a square wave, you take odd harmonics only. So I can add the third and the fifth, say, and make it, there's other things you can do as well. But at any rate, it's very nonlinear. So where do I get these harmonics? So the answer is the device makes them. I mean, look at the current shape. It already is not sinusoidal, right? It's a bump, flat. It has all kinds of harmonics. And so what I do is I drive the device very hard enough that it produces harmonics, because there's diodes inside, right? And then I reflect those harmonics just right to shape the voltage waveform. Or I can shape the current waveform as well, it depends. So there are a number of classes of amplifiers that are called F, F inverse, C, blah, blah, that do this kind of shaping. And what you pick in terms of what you shape depends on the technology you're using. For example, gallium nitride can handle very high voltage. It's a wide bandgap semiconductor, so it can handle high field, which means high voltage. And so what you want to do is you want to actually peak the voltage and square the current. That would be a class F inverse. It's sort of like if you flip the red and the blue here. But other technologies prefer high current, and so you can do this. So it depends. You have to make a choice. When you do that, you have limited, you are stuck. You know, you drive the device and you're stuck with the harmonics you have. So there's not much you can do. We've also had excellent results with amplifiers where we drive them linearly and then we inject the harmonic from the output. Then you maintain linearity. This is terribly nonlinear, so you have to linearize it later. So I'll skip this, but basically this shows an experimental way, because models for transistors that you get don't work for these kinds of regimes. They're made for class AB. And so you have to make your own model, and we make them empirically because we're not good at model making. That's a whole field in itself. And so we're also relatively poor on a US scale. So it's just a small group, you know, and I have to change topics all the time, so I can't invest in expensive equipment. A measurement system called load pool, where you can do this characterization that includes harmonics, is extremely expensive. And so we have, without the harmonics, the system is less expensive. So we have it, and then we figured out a way, at least at low frequencies, how to basically just put a harmonic termination and cut it very carefully with the knife and change the position of the harmonic to find where the optimal frequency is, where the optimal efficiency is. So for example, if you terminate the harmonic right here, you get 77% efficiency for the 7, and if you make a mistake and terminate it here, you lose 10%. 10% efficiency is a big deal for heat. It's not a linear relationship. So it's very important. Further, if you want to do the next harmonic up, we have shown that you can go from 77 to 85%. This is an extremely good result. This is a very good 30-watt amplifier at 2 gigahertz, 85% efficiency, and it was a few years ago when the devices were not as mature. But this just shows that you can really gain something at the third. After the third harmonic, the device gain goes down, and it's a diminishing return because you add loss each time as well. So here's a simple application. So we've done radar as well as communications and all kinds of radar. This is a very interesting. I've picked some stuff that were just interesting applications, you know. This shows the radar that we've made for NCAR, for meteorology, at a practically DC frequency. So I showed you 200 gigahertz almost, and now I'm showing you 0.4, 449 megahertz. But they needed 2.5 kilowatts per array, so a lot more power. The other ones were milliwatts. So this shows 3 antenna arrays, and they look like this. They have 3 panels each. These are circular patches. The arrays themselves are also interesting, but we have papers if you want to see. And this is an interferometer radar. It means that it doesn't scan the beam, but rather you space these antennas and look at the phase shift. And by that, it turns out you can measure all 3 velocities of the wind vector. So this is used for wind profiling in the upper atmosphere. And 449 megahertz is a frequency that was given to this community. So they have to do it very narrow band. Why? Because when you transmit kilowatts of power, they don't want you to transmit over a wide bandwidth. And you actually don't need a wide bandwidth for this. So why do you need that much power? Why do you think? How do you measure? Wind is air, right? So, not clouds. You can measure wind with no clouds, right? Right. So you know, but I don't know my audience. So when you have a wind, you have microturbulences, right? And the microturbulence produces a change in the dielectric constant at the 4th decimal place. So you have to send a lot of power to get anything reflected back, right? The reflection coefficient is very small. And that's why you need tons of power. Plus, you're going up to 5-8 kilometers, above the surface, so it's a big distance. So we wanted to make something that's very portable. See this trailer? The whole radar you can pack in the trailer, and in fact, we have more than just 3 of these. You can have a larger array. So you can have these to be bigger size. What we've done is we made it so that each of these has its own amplifier. Earlier, they had one giant amplifier, and if it failed, and it did fail pretty often, they had to fix the drivers. Then they would be stuck for a while out in the field without their equipment and so on. And so we made it so that each module had its amp, and they had spare modules, and so if they have a problem with one amp, they just replace it. And it needed to be efficient. This was a really fun project. They're out in the field now. I don't keep track of them anymore, but every now and then I get an engineer to call me, well, what capacitor did you use, or. So this shows one of the amplifiers this is one of half this power, because we had to power combine. It uses a single NXP push-pull device. This is LDMOS, because UHF is like a perfect frequency for silicon devices. Perfect. Above that, they don't work that well. It's just great. And these are NXP devices. My student came and said, oh, Zoya, I saw a competition. NXP has a competition, but they give you free devices if you apply. So can I apply to compete? I said, sure, get some. So we got a box full of devices and tested a bunch of them. And then the rule was that you had to send them results. So he made a push-pull amplifier. These are coaxial balance that are easy to make at 449. And we measured it in the lab, and it has harmonic terminations like what I described just earlier, but with capacitors and inductors and some bias lines. And because it's so efficient, we didn't need an extra heatsink. It was very efficient, over 60%. And so we measured it, but I was very worried. This is a lot of power, so we put a lot of attenuators that I borrowed from everybody. And so it's hard to calibrate when you have a lot of attenuators, so I wasn't sure if our results were even good. But we sent them. NXP calls us and says, Brad, to my student, his name is Brad Linseth, Brad, would you you're the finalist, so we're going to fly you to Rhode Island to our facility because we don't trust your measurements, so we're going to measure it. Bring your amplifier. So Brad said, can I go to Rhode Island? I said, sure, go to Rhode Island. So he packed up his amplifiers and went to Rhode Island. And he calls me up and says, wow, we got even better results because we didn't calibrate the attenuators, right? And the other thing that was cool, so that was their setup. He sent me a picture. The other thing that was cool is they put these devices are super robust, so you can short them at the output. He put a screwdriver at the output, which is very bad normally. And the amplifier was alive, so He measured it to be about a 13 VSWR, so basically a short circuit, you know. So, okay, he came back, 2 weeks, we get a call from NXP, you won. We beat Steve Cripps and Boom and Kim. This was really good. Steve is still secretly mad at me about this. Anyway, he got a lot of press, but the ultimate result was we got a lot more devices, so we made a bunch of amplifiers. So this shows, you always worry when you do this high power, you worry what's heating up the most, where your weak link is, so it's a good idea to take a thermal image. And this shows that the device was not heating. Look, it's blue. But there's emissivity here too, but we tried to calibrate for that. But the capacitors were heating. The coax is doing well. The capacitors were really heating. And so in the real amplifiers that they use in the field now, we invested a little more money and bought some better high voltage capacitors so they're not heating as much. The cost of the devices at the time was, I think now it's about 15 cents per watt. So it's getting close to where it would be practical to make a microwave oven out of these. Otherwise, magnetrons are very cheap, right? It's what, $100 per kilowatt? So that's 10 cents per watt. We're not quite there, but it's close. So that's what I want to do. I want to make an array of these and make a microwave oven. Yeah. The trick is, of course, that when you, so these would be good because when you put food, it changes, the loading changes as you cook it. So you need it to survive a screwdriver, you know. Okay, and we got good results. The power added efficiency was over 60%, 65 roughly. And this is the pulse of the radar, so we got a nice clean pulse. Okay, so this radar is frequency modulated inside. It has a chirp, but that's the envelope. So in some sense, it's a very easy waveform for this amplifier because we always operated at the peak efficiency here at the high power. That's not the case in communication. Oh, so these are wind measurements, which I totally don't understand. They have signal processing here, and these arrows tell them the direction, and then they have these little tails, and if there's 3 tails, it's strong wind. If it's 1 tail, it's not strong, and so on. But communication systems don't look anything like that square pulse. They have a horrible, this is a CDMA waveform, WCDMA. Can you see the blue trace here or not? I traced 5 milliseconds of the pulse, and it basically goes like this, you know, all over the place. And this is the envelope, so the amplitude of that vector, and this is the phase. So it's far from constant amplitude, right? In fact, this has about an 8 dB peak to average ratio. So that's bad. Boy, because my amplifier is designed to be very efficient at a high input power, but when the input power varies, it becomes very low efficient, and this is the probability density function of this signal. So I'm always low efficiency, so my average efficiency is terrible. So what I'd really like to do is design an amplifier that follows my waveform, my probability density function. So there's a few ways people do this. This is a very active field of research and a difficult place to compete because all industry is working in it. So if you're doing power amplifiers, you want to do something more exotic, basically. So I've decided that all of the approaches people do are the same. They all have this block diagram. You have a main amplifier, you have some other assisting amplifier, and then you have a division and a combining circuit. So what's done currently in base stations is Doherty. Older base stations have 10% efficiency, which means for every 100 watts, 90 watts is dissipated, and that means you have to cool it, so you have to add more power for the refrigerator. Have you been in a base station? There's big refrigerators in there, so it's huge amounts of power. So if you make the amplifier more efficient, you gain a lot, okay? Which, it's all about cost, right? You're paying for the power. And so now they're Doherty, and they're more efficient, about 30, 35% efficient. And a Doherty amplifier has 2 amplifiers that work at the same frequency at the carrier. But one works all the time, even at low power, and the other one kicks in when you reach a certain power level and it adds power. This sounds easy, but it's not easy to implement properly. So, but this is something that industry has accepted. Usually the drive is digital these days. So you drive it, and then there's a magic combiner here at the output that Doherty made in 1936, I think. So it's not new at all. You know, in the microwave field, it was all done by Faraday, Hertz, Tesla. You know, you're kind of, every time you think you thought of something new, you find that one of these old guys has done it. It's a little bit depressing, but technology changes, you know, so Doherty's amplifiers were with tubes, for example. The other is link outphasing, or link, and this is a technique where you have two amplifiers that are equal, very efficient. So you always operate them at the peak power, but you outphase. So imagine two vectors, right? And you're doing this, and the sum is changing in amplitude. And the trick is how to combine them so that you don't lose the out-of-phase power. This was invented 2 years before Doherty, so it's also a very old technique, outphasing. It's gaining popularity. I think the MIT company is doing that, but they have to assist it. It's not as easy as it sounds because you have to change this phase very, very fast at the signal amplitude, and that turns out to be difficult. And also, it's hard to maintain the efficiency over large angles, so it's a difficult thing. Then there's supply modulation. This is getting a lot of acceptance. Most people call it envelope tracking, but it's really not what they're doing. I'll show you. We've done work in this for the past 10, 12 years, so it's something that I understand reasonably well. We also are doing some outphasing, but different than what the others are. And then there's another class which I won't talk about, but we have a number of papers in this. This is injecting the harmonic. It's beautiful because it maintains linearity, so it's very nice. All of these things are very nonlinear, and you have to linearize them digitally usually. So the question, so look, we've added another amplifier, combining, dividing. The question is, does this pay off? You know, it's expensive, it's complicated. Maybe I'm better off just backing off the amplifier, living with the 10% efficiency and, you know, dealing with it. What is better? So I have to convince people that it does pay off to introduce complexity. So I'll show you that on this example briefly. So this is an example of measured data for a gallium nitride amplifier made in the 250 micron technology, which means you can go up to 36 volts roughly before you kill it. And so this is the efficiency versus power, output power at 32 volts. The green line is at 28. The red one is at 24. So as I change the DC bias, notice that the peak in efficiency moves. And so that means that I can chase the amplitude of the output power waveform by changing the supply voltage. So this sounds really easy, right? So you'll just buy a power supply and change it to this. Well, what's the bandwidth of current comm systems? So LTE is what? 20 megahertz bandwidth. You want multiple channels. OFDM, 100 megahertz bandwidth. Can you go and buy a power supply that can change at 100 megahertz? I mean, they switch at kilohertz, right? So you can't. So this is a hard problem because you've basically, you can make a good amplifier, but then you've given your problem to the power supply people. And the power supply people are not equipped to solve this problem because they're used to kilohertz and things don't scale. Inductors basically don't scale. And so we've been forced to learn. I've had to learn power supplies, which, okay, yeah, they're just also amplifiers in a way. So this is what it looks like. You have to make a good amplifier to begin with. You have to make this power supply. You have to connect it, and then you have to linearize it because it's horribly nonlinear. So it doesn't look like it will pay off. It's way too complicated. Even if you ignore this feedback loop, which is for linearization, you still have all kinds of things to worry about. But it turns out it does pay off, which is really an interesting analysis. So I'll show you. First, you design your power amp. I've kind of explained that already, except because I'm going to change the supply on this amp, I can't use it, I can't characterize it the same way. So what I do is I characterize it over a range of supply voltages, over a range of power levels, over a range of gains, and then I kind of pick a middle, and it's not a unique point. There's a range, but as long as you're in this range, you can digitally adjust the other things to optimize. So I don't know what the optimal solution is, but in some sense I don't care because I can adjust it later. So this is a picture of one of the amplifiers at 2 gigahertz that we've done and some details about it, but anyway. So then we characterize it, which means we measure, these are efficiency curves, so red is good, blue is bad on this scale. And so what I want to do, this is versus supply and this is versus output. So I want to program my supply to follow this line. This just gives me a lookup table for the supply, basically, to make it very, very efficient. And in that process, the gain is nonlinear, so I know ahead of time I have to linearize this thing. But this was a star amplifier in a way. This is not something you can buy. It produced 36 watts. It was measured pulse to get rid of heat. It's just a standard way of measuring it, so it'll have a little less power when it's not pulsed. At 2.1, it had 81% drain efficiency, good gain, 78% power added at 28 volts, and the efficiency was a little higher at a little higher bias, and so on. So, what are the problems? And I have a lot more details about these problems if you ever want, but I'll just tell you now. First of all, you have to have high efficiency for both of these components, the supply and the power amp. So it's two amplifiers basically, but one is UHF at the envelope, at the signal bandwidth, and one is at your carrier. In our case right now, 2 gigahertz, but we do this at 10 and so on. Then this supply has to have a very high slew rate. Bandwidth doesn't make sense when you talk about large signal. Bandwidth is a small signal kind of a measure. What this supply has to do is go from, say, 5 volts to 30 volts very, very quickly. This is very hard to do. Okay, so that's one problem. Then the other problem is the supply sees this amplifier as a load, and the input power and everything is varying. The bias is varying. So you see a very dynamic load. It's a crazy load. This is not what the supply likes to see. No amplifier likes to see a very dynamic load. So, by the way, that's another place where the compression network would be super useful. So, and the third problem is you have all kinds of distortion. This has time-variant linear distortion. This has time-invariant nonlinear distortion. If these two don't travel at the same, don't get to the amplifier at the same time, these two paths, you get another distortion. So it's a mess. You have to linearize. And the message I want to give you is if you ever have to do this, you should identify all of your distortion mechanism by just thinking about it. And then you should figure out how to separately correct each one of them. So for example, this can be done by equalization, so a simple digital filter. You linearize the gain. You just make it flat. It's low frequency. It's doable. This can be done with a static lookup table for AM to PM. Okay, this is what amplifier people are used to, so it's nothing. You just measure it, store the data, and linearize it. Then this can be done by adjusting the delay and monitoring the linearity at the output, and then you fix the delay for the best one. That's the stupidest and easiest thing to do. There are people that develop algorithms for this, but we're not experts in linearization. But this worked. And then you're left over with other nonlinearities, but you can fix those now with digital pre-distortion, except if you did DPD at the beginning, it would have 1 billion terms and you may never converge. This way, you got it down. So here's what happens. You start off with a bad spectrum, and if you do it one by one, you slowly get rid of things, and then at the end, all you do is correct for the nonlinear memory effects with 10 terms in the DPD. So it makes it much more efficient. So here's the answer to the question, did it pay off? Okay. We tested the amplifier, which was a very good amplifier. It was 30% efficient under constant drive, gave 40 watts of peak power, 8.5 watts of average power with this particular modulation that we used, and good linearity. It was linearized, so the transmitter efficiency in this case is 30, the same as the amp, because there's no supply, so you don't have to count the supply efficiency. And we'll say that that's 100% of our heat. So we're comparing our approach to this approach. So this is the heat dissipation. The supply was 28 watts. Now, when I make the amplifier, I drive it always at peak efficiency by varying the supply. I get 76%. The supply was 70%, and this was a patent we did with Texas Instruments, so they implemented the supply in a high voltage silicon process, and I can't show you that. They won't let me. It doesn't matter. We've since made 90% efficient supply, so it can be better even. But with this supply, the system efficiency was 52%, and the consumed power was less. So this is interesting. Okay, we got rid of this amount of consumed power. That's good. That already pays off. But even more interesting, it's divided. There's a red and a blue piece. The red piece is what's dissipated in the amplifier here, and the blue piece is what's dissipated in the supply. It's always good to distribute heat. And so I can promise the RF transistor designer that I will never heat up his transistor. That means I can drive it at a much higher voltage. and it will be much more reliable. The supply parts can certainly handle this amount of power. And so this is the ultimate answer to the question, does it pay off? Yes, it pays off because I win double. I save power, plus I make things more reliable because I'm not operating them very hot. And I think anybody who proposes a high efficiency transmitter should consider this, do a comparison like this. So I think I'll just show you some pretty picture, okay? We've made this at 10 gigahertz on a chip, gallium nitride, and this is a 150 nanometer triquin process that's only now being released, so we got to play with it before it was released, and because I paid them, I could violate the design rules, so we could really push this. You know, they can't tell me don't put two vias this close. I say, why not? I want you to put them that close, so they do it. It's really a great feeling, you know. So anyway, this shows some very efficient high-gain amplifiers. I can tell you they produce 13 watts of output power at 10 gigahertz with almost 70% efficiency and 23 dB gain. So this is like a star amplifier. We're very proud, but of course it's not hard to do when you have the best technology. I mean, it's hard still, but it's what makes it happen. And then these other circuits you see on the side, these are some other exotic test circuits. But these are all power supplies. So we've actually made power supplies in a microwave technology, so it's total overkill. But we need it so that they can be fast. Okay, so how good are these? I can show you. These are the amplifiers that are very good. I just showed you. And this is the power, one of the power supply chips, and it's mounted in a standard package because that's what they wanted us to do. And it's 90% efficient in this package at 14 volts, and then as you drop the voltage, it goes down, but it's still very efficient. This is 85. It will switch up to 100 megahertz, so if we want more bandwidth than this, then we combine it. This is a cascode, so a UHF amplifier that works from basically 10 megahertz out to 500 megahertz with good efficiency. It's not super linear, but we can linearize it fairly easily. So we combine these two to get the bandwidth and the efficiency. And this is a fairly, combining an amplifier with a switcher is a fairly standard approach, but doing it with this kind of bandwidth and power is not standard. So, all right, if you want to see terahertz, you can come by and I can show you. I think I've extended my welcome here at this point. Thank you very much.
You guys working on DPD, so I don't know if you just we just scared them, but with the performance results, but maybe you
no. But the DPD is very useful. I don't know enough about DPD, so since you saw the, are you working on DPD? He was looking at you. So you saw that the gain curve had two slopes, so we just divided the region and did a separate DPD on one and separate on the other. But that was like we read a paper and repeated what was in the paper. So we could use help in DPD. You know, we're not experts in DPD, I'm sorry. But we therefore had to solve all the other problems so that we could do the DPD. We don't know it, yeah.
Well, I have a very, yes? No, go ahead.
There is a lot of stuff now they use around small cells and millimeter wave
Yes.
So have you evaluated whether the power amplifier may apply at millimeter wave?
Do you mean 60 gigahertz or, yeah?
Does that make sense, or not really because the output power is slow?
Well, I can tell you that with this technology in 150 nanometers, you can get close to 10 watts at 25 gigahertz. We got that with 50% or above, so that's quite good. That's better than you could get at 2 gigahertz earlier. At 60 gigahertz, can you ask me again next year? I have a project with Hughes Research Labs in their 60 and smaller process. Right now, we just started. And this is a process that has an FT at 300 gigahertz. So the voltage is, so the problem is that you have to reduce your voltage, okay? But what we want to try to do is use it at actually lower frequencies, like 60, to get very high efficiency. And we're approaching it two different ways, and one is making a fundamental frequency amplifier, so at 60, and the other one is making the amplifier at 20 and then doing a very high efficiency active tripler. So a class E tripler or class F tripler. And my feeling is that it will be better in terms of efficiency and power, because you can stretch a multiplier a little more than a fundamental frequency. Yeah. Well, everybody has, you know, I've been in this business for a number of years now. I don't want to tell you how many. It's depressing. But what I see is that millimeter waves and terahertz have this roughly 5-year popularity cycle. So they'll be popular for 5 years, and then everybody forgets it. And then in about 10 years from the beginning, you know, people reinvent it. And they keep coming up with new applications, but I haven't seen anything really catch on except for car radar. And I think that the chief cause is the atmosphere. It's just very lossy, and also it's cost. You know, it's just very expensive. This huge process costs an arm and a leg.
This is not a CMOS type process, right? So
no, we want more power. So I don't do CMOS because too many people do CMOS, and I just can't compete. I'm only a university, and we're a state school. We're not MIT, you know. I think we're pretty good, but we don't have the money, you know. So I have to stick to things that other people are not really doing. And gallium nitride certainly has the power capability that I think is needed if you're going to make this succeed. CMOS, 10 milliwatts just isn't enough, you know, or 100, whatever they get now. Yeah. But on the other hand, I don't really know. When I went to school, they told me silicon could never work at microwave frequencies because of mobility. And here it is working at 100 gigahertz. So, however, band gap is pretty fundamental, you know. So I'll let you know. I think it's practical but expensive right now. So, what was your question?
well, my question was about the transformer.
Aha.
What is what can you do like a 10-to-1 transformer? Like what is the highest rate of the rate?
So when you do other you have to do a rational number first. That's theoretical. Okay, but doesn't matter. You can always get something close, right? The different transformation ratios will have different number of lines in between, because you do different series parallel combinations. And 10-to-1, I think you need, yeah, you can do 10-to-1. You need
I might sacrificing bandwidth, but
yeah, it won't be decades, but it will be still pretty broadband. I've done this. I think you need 4 lines for 10-to-1. I can send you. I sketched it, so I can send you the sketch. But I forgot. There is a non-intuitive trick to do the 10-to-1. If you want to minimize the number of lines, because if you do a standard one, it's too many, 6 or something. Yeah. But yeah, you can. Yeah. They're cool. Thank you very much.
Thank you.